reset. I wonder if it'll just make that one go back down.
I think. Yeah. There we go. Now, what's the next option here?
Let's see, we'll start. Engine 1 start control valve stuck open. That's a good one.
Okay.
I think. Let me read this real quick. Open SIG mechanical. Take a look. Yeah, we don't want that. See this one.
Is it the starter SOV shut-off valve?
Since it represents a full mechanical stud in the starter control valves during start, SCV will only close the ground.
Some aircraft are equipped with thrust reversers. The thrust reverser is designed to redirect exhaust gases forward and outward to help aircraft deceleration. The thrust reversers are used for ground operations only. When the thrust reversers are stowed, they are part of the exhaust nozzle. The thrust reverser system consists of electric controls and indications, a hydromechanical actuation system, and 2 pivoting doors. A lock protection system prevents inadvertent in-flight actuation of the thrust reversers. The actuators and thrust reverser doors are mechanically locked in the stowed position by 3 locks. These locks are called the primary, the secondary, and the tertiary locks. In the normal stowed position, the primary lock maintains the thrust reverser doors closed, and the secondary and tertiary locks are unloaded. The primary and secondary locks are electrically controlled and hydraulically actuated. Once actuated, they unlock the associated door. The tertiary lock is electrically controlled and actuated. The tertiary lock provides a fully independent locking system. Once actuated, this tertiary lock unlocks the associated door. Thrust reverser deployment is commanded by the backward movement of the associated thrust lever. This removes the mechanical locks and hydraulic pressure is used to deploy the thrust reverser doors. After pivoting, the rearmost part of the doors blocks the normal exhaust gas path, and this gas is then redirected forward and outward. The FADECs control the operation of the associated thrust reverser. When the thrust lever is below idle during landing, the FADEC will command reverse thrust only after the thrust reverser doors on both engines are completely deployed. In the event one engine is inoperative, or the thrust reverser on one side is not deployed, the FADEC on the operating side will command reverse thrust provided the associated thrust lever is requesting reverse thrust and the thrust lever on the affected side is at idle. The FADECs will command maximum reverse thrust only when the aircraft is on the ground, provided the associated thrust lever is requesting reverse thrust, the associated thrust reverser is deployed, and either condition exists. Both main landing gears are indicating that the aircraft is on the ground, and the main landing gear wheel speeds are greater than 25 knots, or all 3 landing gear are indicating that the aircraft is on the ground. Thrust reverser deployment is indicated on the ICAS. Each engine is controlled by 2 FADECs referred to as FADEC A and FADEC B. The system is designed so that all signals between the FADECs, the engine, and the aircraft are completely redundant. Both FADECs alternate for control of the engine. When one is in control, the other remains in standby. While in standby, the FADEC still monitors the normal inputs and still performs built-in test and fault detection. However, the outputs for fuel flow and CVG control are powered off. Each FADEC receives commands from the control pedestal and from the power plant control panel and sends commands to the FPMU torque motor, which meters the fuel flow to the engine so as to reach the N1 speed calculated by the FADEC thrust management section. The air data computers provide airspeed and temperature information, which are used by the FADEC to calculate the maximum available thrust for the selected thrust rating mode. Each FADEC performs the following functions: fan speed control, CVG control, ITT limiting, overspeed protection, thrust management, ignition control, start-stop control, auto relight, FADEC reversion, engine monitoring, ITT trim, and air conditioning packs. An internacelle data bus provides a means of communication between each side's FADECs. The internacelle bus provides three main functions: fan speed synchronization, ATTCS, and data difference checks. A FADEC transfer of control occurs for one of the following reasons: loss of electrical power, hardware faults, loss of N2 signal, inability to control the CVG, or manually through the FADEC selector knob. The engine control system consists of two FADECs, fuel pump and metering unit, or FPMU, permanent magnet alternator, or PMA, control pedestal, and a power plant control panel. The two functions of the power plant control system are engine control and thrust management. The engine control logic receives fan speed request and controls the engine fuel in CVG. The control logic incorporates protection logic to prevent engine damage from speed or temperature exceedances. The primary control mode of the engine is a closed-loop fan speed control. When the thrust management logic requests a certain N1 speed, the difference between the actual and commanded fan speed is used to adjust the fuel flow so as to achieve the target N1 speed. The engine control logic also controls the compressor variable geometry, or CVG vanes. The FADEC adjusts the vanes in response to the N2 speed so as to maintain the optimum compressor efficiency and maintain an adequate stall margin during transients. The FADEC calculates the maximum available engine thrust for a given thrust rating mode, airspeed, ambient conditions, and bleed air configuration. TO1 corresponds to an N1 target provided to the ICAS and indicated as a cyan bug on the N1 analog indicator, except in the alternate TO1 mode where it indicates the alternate TO1 thrust setting. When the thrust lever is set to the thrust set position, the FADEC controls the engine at the N1 target. The FADEC uses the following data as primary reference to calculate N1: pressure, altitude, and Mach number from the ADCs, reference takeoff temperature during takeoff, ADC total air temperature in flight, reference anti-ice during takeoff, and anti-ice system feedback in flight. Engine thrust rating mode selection is done using the thrust rating buttons on the center pedestal. The available modes are takeoff thrust, maximum continuous thrust, climb thrust, cruise thrust. Click on the Takeoff Thrust button to continue. TO1, or takeoff mode, represents 100% of the available thrust. This mode is limited to a maximum of 5 minutes. The FADEC will select the takeoff mode if any of the following occurs: FADEC power-up or power interruption, TO1 is selected during the takeoff data setting procedure, the TO1 mode button is pressed, the thrust lever is moved beyond the thrust set position, the gear is down and locked below 15,000 feet, or both engines do not agree on the thrust mode for 340 milliseconds. The alternate takeoff mode represents 90% of the available thrust. This mode is set through the overhead panel with takeoff data setting procedures. The continuous, or maximum continuous mode, is 80% of the available thrust. It is the highest thrust setting you can run the engine at, such as an engine out situation. Continuous is selected any time maximum continuous thrust is needed. Click on the Continuous button to continue. The continuous mode is available when the aircraft is 300 feet above the takeoff altitude and the gear is not locked down, or when the aircraft is 1,700 feet above takeoff altitude. The climb mode is approximately 76% of the available thrust. It is inhibited on the ground or during a single engine situation. Climb thrust is available when the pressure altitude is greater than 500 feet above takeoff altitude and there is no landing gear down and locked signal, or when the pressure altitude is greater than 1,700 feet above takeoff altitude. The cruise mode is approximately 70% of the available thrust and is the maximum cruise thrust. It is inhibited on the ground or during a single engine situation. Cruise thrust is available when the pressure altitude is greater than 500 feet above takeoff altitude and there is no landing gear down and lock signal, or when pressure altitude is greater than 1,700 feet above takeoff altitude. The takeoff data is set on the MFD takeoff page. To set the takeoff data, you'll need to set the thrust setting TO1 or alternate TO1, the ambient temperature from ATIS or a reliable source, and anti-ice on or off. You'll get an ICAS message, no takeoff data, if you forget to enter takeoff data. If the takeoff data is acceptable, it will be displayed in blue. If the takeoff data is not accepted, it will be displayed in amber. To enter takeoff data, press the Store button on the engine control panel. An arrow will appear on the right-hand side of the takeoff data. Click on the Store button to store the data. After the first pressing of the Store button, the MFD indicates the following values: takeoff mode TO1, the reference takeoff temperature, either T2 synthesized if the engine is running, or ISA if the engine is not running. T2 synthesized is the synthesized total air temperature at the engine fan inlet based on the fan discharge total air temperature and N1. And the reference anti-ice status. When using anti-ice, thrust is decreased by approximately 3%. The FADEC automatically compensates as the anti-ice valves open. The cursor is first positioned next to the TO1. To select alternate TO1, use the Increase-Decrease knob on the overhead panel. Click on the Increase-Decrease knob to change your selection. Pressing the Store button a second time places the cursor on the reference takeoff temperature line. By rotating the Increase-Decrease knob, you will change the reference takeoff temperature. Once again, push the Store button to save and move to the reference anti-ice on or off line. The default for the engine reference anti-ice is off. To turn it on, use the increase-decrease knob. Press the Store button a fourth time to store the entries. The cursor will disappear. If the information is accepted and an engine is running, all the data will turn cyan. If no engine is running, the data will stay amber until you start an engine and then turn cyan. If an engine is running and the data stays amber, that means it wasn't accepted by the FADEC. The FADEC wants the temperature you enter to be within 10 degrees Celsius of what it thinks it is. If there is a disagreement, an ICAS message will be presented. If no data is entered, or if the data is entered incorrectly, an ICAS message, Engine No Takeoff Data, will appear. If there is an engine failure during a takeoff with alternate TO1 selected, the Automatic Takeoff Thrust Control System, or ATTCS, automatically resets the thrust on the remaining engine from alternate takeoff thrust to maximum takeoff thrust, or TO1. The ATTCS is armed with alternate TO1 selected, the airplane on the ground, engines running, the thrust levers set to 45 degrees or higher, and both engines are ATTCS capable. The ATTCS is disarmed if alternate TO1 mode is deselected, if after being armed the thrust levers are reduced below 42 degrees, or the ATTCS is triggered. If a thrust lever is moved beyond the thrust set position, the FADEC automatically commands the engine to the maximum available thrust in the TO1 mode. If the ATTCS is armed, and either FADEC A or FADEC B detects a failure of the other engine, the controlling FADEC will command the operating engine to the TO1 mode. The N1 target calculated by the FADEC is based on data input by the flight crew. The N1 is depicted by different icons. A blue T is the target N1. A green diamond is the N1 requested by the associated thrust lever. A green line is the current N1 value. The N1 request is a function of the N1 target and the thrust lever angle, or TLA. The table depicted here indicates the N1 requests for the various thrust lever positions. In the event of a total loss of N1 from both FADECs, the FADECs will derive a synthesized N1 as a function of N2 and ambient conditions. This mode is referred to as an N1 reversionary mode. When this occurs, the N1 indication is replaced with amber dashes. The maximum available thrust is calculated by the FADEC according to the thrust rating mode, the airspeed or Mach number, the ambient conditions, and the bleed air configuration. There is only one idle position on the thrust lever control pedestal, but there are two different idle ratings set by the FADEC. The purpose of the ground idle speed is to avoid engine flameouts, overtemperature, or an inability to accelerate, provide the required bleed air for the environmental control system, as well as provide the required speed to drive the accessories. Ground idle speed is determined by the ambient temperature and is commanded when the aircraft is on the ground. The purpose of the flight idle regime is to avoid engine flameouts, overtemperature, or an inability to accelerate, provide the required bleed air for the ECS and the anti-icing system, and enable the engine to accelerate from flight idle to 95% TO1 thrust in 8 seconds at or below 9,500 feet. We will now look at the controls and indicators associated with the engines. The gust lock lever on the center pedestal prevents the movement of the thrust levers forward of the idle position when it is set in the locked position. This position also serves as a gust lock and prevents the movement of the elevator control surfaces. The thrust levers are used to set the desired thrust. When the thrust levers are in the idle position, the FADECs command the engines to produce either ground or flight idle. The maximum position commands the maximum thrust rating. Positions in between idle and maximum are used to set the target N1. The N1 target set by the thrust lever is indicated on the corresponding N1 indication of the ICAS by a green triangle. The resistance to the thrust lever movement can be adjusted by rotating the friction lock knob clockwise. Rotating the knob counterclockwise decreases the amount of friction. The desired thrust rating mode is selected by the thrust rating control panel. The takeoff button is used to set the maximum takeoff thrust mode. The continuous button selects the maximum continuous thrust mode. The climb mode selects the maximum climb thrust mode of operation. The cruise button selects the maximum cruise thrust operation mode. Ignition, FADEC, takeoff data, and engine start functions are handled by the power plant control panel on the overhead panel. Engine ignition is controlled by the 3-position ignition knob. The positions are off, auto, and on. In off, the ignition system is de-energized. In the on position, the FADECs are commanded to provide continuous ignition through the 2 ignition channels. There is no time limitation on the use of the ignition. In the auto position, the FADECs automatically produce continuous ignition depending on the engine requirements. One igniter is energized during a start on the ground, and both igniters are energized for an air start or if a flameout has been detected. A 3-position FADEC knob provides control of the 2 FADECs associated with each engine. This knob is spring-loaded to the center position. Momentarily placing the knob in the reset position resets the FADECs and clears any faults. Click on the number 2 FADEC knob to continue. Momentarily placing the knob in the alternate position enables the FADEC in the standby mode to take control of the associated engine. The FADEC knob becomes inoperative if it is held in either position for more than 3 seconds. The takeoff data is set by the Store button and the Set knob. Click on the Store button to continue. The first press of the Store button places the cursor in the takeoff mode line. The second press of the Store button places the cursor on the reference takeoff temperature line and enables the reference temperature to be changed. Click on the Store button to move the cursor to the reference takeoff temperature line. The third press of the Store button places the cursor on the reference anti-ice line and enables the engine anti-ice status to be changed. If the reference temperature is within limits, The fourth press of the Store button accepts the data. The Takeoff Data Store button becomes inoperative if it is held in for more than 3 seconds. The Takeoff Data Set control knob is used to set the takeoff mode, the reference temperature, and the anti-ice condition. The cursor indicates which of the two values can be changed by the knob. In order to change a value, the knob must be pressed and turned in the increase or decrease direction. When the cursor is set at the takeoff mode line, the knob can be used to set alternate takeoff 1 or takeoff 1 alternately. When changing the reference temperature, a momentary actuation in either direction changes the temperature in 1-degree increments. If the set knob is held for more than 1 second, the temperature changes 5 degrees per second. When the cursor is set at the anti-ice line, the knob can be used to set the anti-ice initial condition on or off. Engine start is controlled by the Start-Stop knob. This knob has 3 positions: Stop, Start, and Run. Placing a Start-Stop button in the Stop position commands the FADEC to shut down the engine. The spring-loaded Start position is used to start the engine. If the Start-Stop knob is held in the Start position for more than 3 seconds, the knob will become inoperative. In order to regain control of the Start-Stop knob, you will need to reset the associated FADEC by means of the FADEC control knob. The Start-Stop knob spring loads to the Run position. This is the normal position for normal operations. We will now look at the ICAS indications associated with the engines. The N1 target indication is indicated by a cyan T on the N1 dial. The equivalent numerical value is displayed in cyan above the gauge. This value corresponds to the maximum thrust for a given thrust rating mode with the thrust levers in the thrust set position. It ranges in value between 0 and 100% and is displayed with a resolution of 0.1%. The N1 target is removed from view when its value is less than 0 or greater than 100%. The N1 indication displays the N1 speed in percent. The scale ranges from 0 to 100%. The current N1 speed is numerically displayed in a box. The needle indicates the N1 speed on the dial. The N1 indications are displayed in green for values in between 0 to 99.9%. For values at or above 100%, the dial, needle, and digits turn red. The selected thrust rating mode is displayed in between the two N1 gauges at the top of the display. The selected mode is displayed in cyan. The FADEC in control of each engine is displayed next to the N1 gauge. The labels can be either A or B and are displayed in green. The N1 requested by a thrust lever is displayed on the corresponding N1 gauge. This N1 request bug is a solid green triangle. The acceptable range for the N1 request is 0 to 100%. The indications are removed for requests greater than 100% or less than 0%. The enabled ignition channel is indicated by a green label between the N1 and ITT gauges. The acceptable values are ignition A, ignition B, ignition AB, or ignition off. The interturbine temperature, or ITT, is indicated on the ITT gauge immediately below the N1 gauge. During engine start, the scale is green between 300 and 800 degrees Celsius. The red line starts at 801 degrees Celsius. During the takeoff mode, the green range is between 300 and 921 degrees Celsius. For the EP model, the red line is at 920. For the continuous, climb, and cruise modes, the green range is between. If the red range is exceeded, the temperature is indicated by digits and an analog pointer. The digits range in value between -65 and 1999 degrees Celsius and are displayed with a resolution of 1 degree. The color of the digits mimics the color of the scale. The N2 speed is numerically displayed below the ITT information. The N2 speed ranges from 0 to 120% and is displayed with a resolution of 0.1%. For speeds between 0 and 102.4%, the digits are displayed in green. For speeds above 102.4%, the digits are displayed in red. Fuel flow information is displayed below the N2 speed. The fuel flow values range from 0 to 4,000 pounds per hour. The resolution is 10 pounds per hour. The fuel flow information is displayed in green. Engine vibration information is displayed in the lower right-hand side of the ICAS screen. The left scale indicates the vibration of the low-pressure shaft, and the right scale indicates the vibration of the high-pressure shaft. The vibration values range from 0 to 2.5 inches per second. For the low-pressure shaft, the vibration reading is displayed in green for values between 0 and 1.8 inches per second. Above 1.8, the values are displayed in amber. For the high-pressure shaft, the vibration reading is displayed in green for values between 0 and 1.1 inches per second. Above 1.1, the values are displayed in amber. The oil temperature is indicated by a pointer on a vertical analog scale and numerically. The oil temperature indications range from 0 to 180 degrees Celsius in 1 degree increments. The scale, pointer, and digits are displayed in green when the oil temperature is between 21 to 126 degrees Celsius. For values below 21, the scale, pointer, and digits are displayed in amber. For values above 126 degrees Celsius, the scale, pointer, and digits are displayed in red. The oil pressure is indicated on a vertical analog scale and numerically. The oil pressure indication can range from 0 to 99 psi in 1 psi increments. The color of the scale, pointer, and digits depends on the N2 speed. The scale, pointer, and digits are displayed in red when the oil pressure is below 34 psi. When N2 is less than 88%, the scale, pointer, and digits are displayed in green for values between 34 and 110 psi. The scale, pointer, and digits are displayed in amber when the corresponding oil pressure is above 110 psi. When the N2 is above 88% and the oil pressure is between 34 to 49 psi, or between 110 to 155 psi, the scale, pointer, and digits are displayed in amber. When the N2 is above 88%, the oil pressure scale, pointer, and digits are green when the oil pressure is between 50 to 110 psi. Engine information is also displayed on the MFD takeoff page. The takeoff mode indication is displayed in the first line. The indications can be either takeoff 1 or alternate takeoff 1. the indication is removed while the aircraft is in flight. The reference takeoff temperature is displayed on the second line. The indication is removed while the aircraft is in flight. The reference anti-ice status is displayed in the third line. The status can be either on or off. The anti-ice reference is removed from the display when the aircraft is in flight. The oil quantity in each engine is displayed in the bottom line. The values range from 0 to 13 quarts for the left engine and 0 to 14 quarts for the right engine in 1 quart increments. For values above 6 quarts, the oil quantity is displayed in green. For quantities below 6 quarts, the indication is displayed in amber. Engine information is also displayed on the first engine backup page on the RMU. This page provides N1, ITT, N2, fuel flow, oil pressure, and oil temperature indications. The N1 indications are displayed numerically and on a vertical analog scale. The color logic of this page is similar to the ICAS colors. We will now review the various ICAS messages associated with the power plants. An Engine 1-2 out warning message indicates that both N2 RPMs have dropped below 8,500 RPM uncommanded. An ATTCS failure warning message indicates an ATTCS failure associated with a low N1. An Engine 1 or 2 ATTCS no margin warning message indicates that the associated engine has no ITT margin to achieve the TO1 thrust if the ATTCS is triggered. An Engine 1 or 2 oil low pressure warning indicates that the oil pressure in the associated engine has dropped below 34 psi while the engine is running. It can also indicate that the respective pressure switch has failed in the closed position when the engine is not running. An Engine 1 or 2 low N1 warning message indicates that the associated engine does not achieve the requested N1. An Engine 1 or 2 fuel low temperature caution message indicates that the fuel temperature in the associated engine is below 5 degrees Celsius. An Engine 1 or 2 ATS shutoff valve open caution message indicates that the associated engine ATS shutoff valve is open and the N2 speed is above 53%. An engine reference anti-ice disagree caution message indicates that there is a disagreement between the reference anti-ice selected by the crew and the actual anti-ice system configuration. An Engine 1 or 2 Control A or B failure caution message indicates that there is a failure of the respective control system in the associated engine. An Engine 1 or 2 Control Failure Caution message indicates that a failure has been detected in the engine control system. An Engine 1 or 2 TLA Failure Caution message indicates a failure of the associated thrust lever angle sensor. An Engine No Takeoff Data Caution message is displayed when the N2 speed is above 53% and the takeoff data has not been successfully entered. A FADEC ID No Dispatch Caution message indicates that a different FADEC application is installed on the aircraft. An Engine 1 or 2 Out Caution message indicates that the associated N2 has dropped below 8,500 RPM uncommanded. An Engine 1 or 2 No Dispatch Caution message indicates that the Associated FADEC has detected a no dispatch condition in the associated engine. An engine 1 or 2 exceedance caution message indicates there has been an ITT or N2 exceedance that was detected during the previous flight. An engine 1 or 2 FPMU no dispatch caution message indicates that an incompatible FPMU has been installed in the associated AE1 engine. An engine 1 or 2 reverser fail caution message indicates that the thrust reverser doors are not stowed and in transit with the thrust levers set at or above idle, or the thrust levers are set below idle while in flight. An engine 1 or 2 reverser disagree caution message indicates one of the following situations. At least one thrust reverser door is not fully open, the thrust reverser system is not isolated from the hydraulic system, or there is a door locking or position switch signal failure with the thrust levers set at or above idle. An engine 1 or 2 oil impending bypass advisory message indicates that the differential pressure across the oil filter exceeds 22 psi. An engine 1 or 2 fuel impending bypass advisory message indicates that the differential pressure across the fuel filter exceeds 11 psi. An engine 1 or 2 ADC data failure advisory message is displayed when data from both ADCs is lost or a synthesized T2 is used as a temperature source. An engine 1 or 2 FADEC fault advisory message indicates that a FADEC fault has been detected. An engine 1 or 2 idle stop failure advisory message indicates that the idle stop has failed. Watch the turbofan malfunction recognition video.
Today's jet transport engines are the most reliable and powerful aircraft engines ever developed. Over the past 40 years, technological improvements have increased the amount of thrust, improved fuel consumption, reduced noise, and reduced unwanted emissions. To accomplish these advances, internal engine pressure has been greatly increased on today's high-bypass turbofan engines. The reliability of the gas turbine engine has reached a level where severe engine failure is so unlikely that most pilots will never experience one in their flying career. However, modern turbine engines can still fail. And when they fail, whether with a loud bang and high vibration or just quietly decay to zero thrust, the pilot is expected to recognize the specific engine problem and then to take appropriate action. Over the last several years, data has indicated some pilots have attempted to diagnose aircraft malfunctions prior to establishing control of the aircraft. This has occurred despite the fact that all pilots are taught to fly the aircraft first. So why does the data indicate that they have not done this? One of the main reasons is the startle factor. Because of modern aircraft's high reliability, when a malfunction occurs, it is frequently the first time the flight crew is exposed to the true sensations of that malfunction. While simulators have greatly improved pilot training, they've not always realistically simulated the actual noise, vibration, and aerodynamic forces certain engine malfunctions cause. It also appears that the greater the physical sensations the pilot feels during the malfunction, the greater the startle factor. And the greater the likelihood the flight crew will try to diagnose the problem immediately instead of flying the aircraft first. When flight crews are interviewed after engine malfunction events, such as the surge of a large high-bypass engine during initial climb-out, they make very similar comments regarding the event. Pilots will often report that it felt like a bomb went off, or that the aircraft was falling apart. Each time an event occurred, the sound and the feel of the event were different, and often much more intense than indicated by any training the crews had received. Because of this, the flight crew either did not recognize the engine symptom or was so concerned about the engine that they responded without taking time to correctly evaluate the situation. In each case, additional time spent in stabilizing the airplane's flight path before responding to the engine symptom would have avoided a serious event. Remember, all transport category aircraft are designed and certified to be controllable with the most critical engine failed. Unlike early turboprops, turbofan-powered airplanes do not require immediate pilot action to the engine in the event of a single engine malfunction or failure. Once the flight path is stabilized, the engine malfunction may be safely identified and the appropriate checklists executed. Taking the time to stabilize the flight path may sometimes lead to further engine damage, but despite that, the airplane still has the capability of safe flight. Engines are tested during initial certification to demonstrate ruggedness following bird and ice ingestion. Even after a major failure, such as the loss of an entire fan blade, which is an extremely rare event, the engine shuts down safely and the airplane is still airworthy. Service history of fleet aircraft verifies that there are generally no engine failures requiring an instant engine shutdown in order to maintain airplane safety, and that continuing a takeoff after an engine failure at V1 is safer than rejecting the takeoff. So, the capability to recognize turbine engine malfunctions must be learned. But how? The objective of this video is to provide pilots with information to help them recognize and identify various engine malfunctions that have led to inappropriate crew responses and accidents in the past. These malfunctions include fire warnings, tailpipe fires, bird strikes, vibration, engine surge, severe engine damage, and slow power loss. In each case, the first priority is to employ the basic stick and rudder inputs necessary to maintain aerodynamic control of the aircraft. Remember, fly the airplane and then identify and respond to the engine malfunction when time permits. Fire warnings result from excessively high temperature in the space between the engine casings and cowling or from fire detection system malfunctions. The heat source may be an actual fire around the engine, an engine failure allowing core air to escape through a hole in the casings, or a leak of hot air from a bleed duct. Whenever a fire warning occurs, the first priority must be to fly the airplane. Once the airplane is stabilized, attention should then be directed toward execution of the appropriate checklist. Even if there is an actual fire, there is adequate isolation between the airplane structure and the nacelle to ensure sufficient time to establish and maintain airplane control to a safe altitude. Taking this time may cause further fire damage within the nacelle, but accident reports consistently show that flight path control must be focused on first, and it must remain a high priority until landing. Engine torching, or tailpipe fires, mostly occur during an abnormal engine start, but they may also occur after shutdown or during other ground operations. Although there may be no cockpit engine instrument indication, these events can be very spectacular when viewed from the ramp or cabin, and have been confused with an actual engine fire. The torching may be of short duration or it may last for several seconds. Note that the flame is confined to the tailpipe. Flames may turn upward and threaten the wing if no airflow is maintained through the engine, and in some cases, an EGT increase may be indicated on the flight deck. Simply cutting fuel flow while continuing to motor the engine normally extinguishes the flames. The flight crew depends on ground personnel to identify engine torching. If you are told of an engine fire without any flight deck indications of a fire, follow the engine torching procedure as outlined in your flight manual. This procedure will direct you to motor the engine and extinguish the flames. The regular fire procedure will not. Do not perform the engine fire procedure unless a fire warning indication occurs. Executing the regular fire procedure may disable bleed air to the engine starter and prevent you from being able to motor the engine to blow out the tailpipe fire. There have been cases where flight attendants or passengers have initiated evacuations due to engine torching. These unnecessary evacuations can be minimized by prompt flight deck and cabin crew coordination to provide passengers with pertinent information and to alleviate their concerns. Bird strike is a concern for every pilot. The birds may be observed by the flight crew, or the first indication of a bird ingestion may be an engine surge. Flocking birds are a particular concern since they can affect more than one engine. It may be difficult to see the birds and to know how many engines have ingested birds.
V1, rotate. Birds.
I check the birds.
Come on, baby. Keep flying.
Keep going now.
Keep flying. Positive rate.
Yeah.
Come on, baby. That's it. Nice job. Fly the airplane. There's 400 feet.
Okay, what's the problem?
Most bird strikes occur close to the ground, at the very time when there is least opportunity to appraise the situation. Nevertheless, the record shows that establishing flight path control first before taking action on the engine is a more successful strategy than taking immediate action with the engine. There have been accidents resulting from bird strike-related rejected takeoffs above V1 speed, and in each case, the airplane was in fact safe to fly. Therefore, rejecting a takeoff due to a bird strike at speeds above V1 is not considered to be appropriate. Bird strike by an engine may be accompanied by audible thuds, vibration, engine surge, unpleasant odors, and abnormal engine instrument readings such as high EGT. Throttling back an engine may be needed to clear a stall after the airplane has been placed on a stable flight path. If the engine involved cannot be positively identified, do not shut it down. In the unlikely event of multiple engines surging, prompt action may be required to clear the stall on the engines one at a time, to assure that some power is available later. Engine vibration may be caused by a fan unbalance. This can come from ice buildup. It may also come from the fan blade material loss or aerodynamic excitation from blade distortion due to foreign object damage. Vibration can also come from internal engine failure such as a bearing failure. Cross-reference of all engine parameters will help to establish whether an engine failure actually exists. Engine-induced vibration felt on the flight deck may not be indicated on instruments. For some engine failures, severe vibration may be experienced after the engine has been shut down to the point where instruments are difficult to read. This vibration is caused by the unbalanced fan, windmilling at an engine speed close to an airframe's natural frequency, which amplifies the vibration. Changing airspeed and/or altitude will change the fan windmill speed, and an airplane speed may be found where there will be much less vibration. There is no risk of an airplane structural failure due to vibratory engine loads during this windmilling action. From a flight crew member's perspective, one of the most startling events is the engine surge or stall on takeoff or during flight. An engine surge is, in the simplest terms, the breakdown of the airflow in a turbine engine. When the compressor blades stall, they are no longer able to force the air through the engine from front to rear. Now the high-pressure air in the middle of the engine can escape explosively from front and back simultaneously. Usually there are visible flames from both ends of the engine, accompanied with one or more very loud bangs. This violent airflow reversal will produce an instant loss of thrust and an immediate yaw that will literally spill most of the coffee from your cup. This yaw is accompanied by a vibration that cannot be duplicated in the simulator. Bird strikes, internal engine failures, engine pneumatic bleed malfunctions, or internal engine clearance changes can cause a surge. It is usually a problem in the compressor system and so is often referred to as a compressor surge or compressor stall. The magnitude of the symptoms, such as the loudness of the noise and the severity of the vibration, vary with the power setting and the type of instability in the compression system. Low altitude and high power settings produce the loudest bangs and the most violent yaw and vibration. High altitude surges are frequently associated with engine power changes during leveling off or when initiating an altitude change. High-altitude surges generally result in a muffled noise, light vibration, and increasing EGT, and may require power reduction to clear the condition. Some surges allow the engine to recover with no flight crew action. Others recover after flight crew action to reduce power. The most severe surges are non-recoverable. When the engine recovers by itself, it is best to just fly the airplane and not interfere with the engine. Identification of a recoverable compressor surge or stall condition based on engine parameter fluctuations or changes alone can be difficult, due in part to the fact that the event is usually over in the blink of an eye. Generally, most flight crews identify the condition as an engine malfunction when the EGT exceeds its limits or the EGT gauge turns red. If EGT continues to rise following a surge, the thrust lever should be retarded to allow the engine to recover. Then, after the engine recovers, power should be reapplied slowly. If the engine does not stall again when the power lever is readvanced, the power can be left high. If the engine stalls again with the reapplication of power lever input, the power setting may need to be left at a lower power or idle condition. Continue to fly the airplane to ensure the indications return to normal. If the engine does not recover or the EGT remains out of limits, then a shutdown of the engine may be the logical choice depending on the operational situation. Your flight manual and checklists identify the specific procedures to follow. Remember that an engine at idle still provides power for airplane systems and creates less drag than if shut down. There have been numerous occasions where a high-power compressor surge has occurred during the takeoff roll or initial climb-out, and the flight crew was notified by the tower that an engine was on fire. As a result, the flight crews accomplished the engine fire checklist and shut down the engine, even though there was no fire warning enunciated in the cockpit. The tower saw fire out the inlet and tailpipe, and their information regarding seeing flames outside the engine was correct. But an engine shutdown was not necessary since this was not actually an aircraft fire. While the likelihood of high-power engine surge is rare, the startle factor associated with loud bangs and airplane vibration has led to instances of inappropriate action such as rejecting the takeoff after the V1 speed, shutting down the wrong engine, improperly executing the failure climb profile, or failing to comply with established ground tracks to clear rising terrain. Only take action to address the surge after stabilizing the flight path. Recent interviews with pilots who have experienced high-power compressor surge malfunctions during takeoff and initial climb have revealed that they have initially thought that a bomb had exploded, or that they hit a truck, or had a mid-air collision. Remember, no matter how loud the bang, airplane control is always the first priority. In the event of a major internal engine failure resulting in severe engine damage, there may be a variety of symptoms on the flight deck. Fire warnings, engine surge, vibration, high EGT, fluctuating RPM, oil system parameters out of limits, and thrust loss. Any one of these symptoms alone could be from a more benign malfunction, but multiple symptoms are a good indication of severe engine damage, and visual inspection by the cabin crew can be very helpful in confirming this. Visual symptoms may include flames, smoke, or visual damage to engine cowlings. It may not be possible to distinguish initially between an engine surge without damage and one accompanying severe damage. The symptoms of the two kinds of events can be very similar, and from an operational standpoint, it is not important to know immediately which of the two has occurred. If it does become necessary to shut down the engine, wait until you positively identify the engine you select as actually being the malfunctioning engine. It should be noted that even an engine which may show signs of visible damage and visible flames may very well be producing useful power necessary for initial climb-out. Again, the first priority is to fly the airplane, not the engine. After you have positive control of the aircraft's flight path, then identify and secure the affected engine when time permits. Diagnosis of exactly what caused the engine problem is neither necessary nor safe. if it diverts resources from flying the airplane. The malfunctions discussed so far have compelling cues, such as loud bangs, vibration, and warning or advisory messages. In each case, the challenge is to fly the airplane without being distracted by very compelling or alarming engine symptoms. The last type of malfunction to be discussed here is more subtle: slow decay of thrust, or non-response to power lever. These can be subtle in fact to the point that it can be completely overlooked, with potentially serious consequences to the airplane. If an engine slowly reduces power, or when the thrust lever is moved the engine does not respond, then the airplane will experience asymmetric thrust. The problems will most likely develop at a point during the flight when the autopilot is engaged. The autopilot will compensate for the asymmetrical thrust on its own. It takes an alert flight crew to recognize the situation that's developing. If the airplane is badly mistrimmed when the autopilot is manually disconnected, or when the autopilot reaches the limits of its authority and automatically disconnects, only seconds remain before an unusual attitude is encountered. If no external visual references are available, such as flying over the water at night or an IMC, the likelihood of an upset increases. This condition of low-power engine loss with the autopilot on has caused several aircraft upsets, which were not always recoverable. Flight control displacement or trim input indicators may be the only obvious indication that the autopilot is trimming the aircraft away from the coordinated flight. Vigilance is required to detect these stealthy engine malfunctions and to maintain a safe flight attitude while the situation is still recoverable. But a slowly changing asymmetric thrust problem is not an easy one to detect. Symptoms may include multiple system problems such as generators dropping offline, low engine oil pressure, unexplained airplane attitude changes, significant differences between primary parameters from one engine to the next. If asymmetric thrust is suspected, the pilot must be prepared to make immediate rudder or trim inputs to avoid an uncommanded aircraft roll. The first response must be to make the appropriate rudder input or trim adjustment. Disconnecting the autopilot without appropriate control input or trim adjustments may result in a rapid roll maneuver. Different aircraft from different airframe manufacturers display different types of indicators to the pilot regarding the amount of trim the autopilot may be adding to the system. Consult your flight manual and training department to gain a full understanding of how your particular aircraft provides visual, audible, or tactile indications of the amount of trim being added by the autopilot. The sequence of events and severity of symptoms experienced during an engine malfunction may vary from the events shown in this video and from those experienced in a simulator. Engine malfunctions vary from one event to the next. The failures shown here were selected as relatively severe, but not the most severe that have ever occurred. Simulation of failures may be limited by simulator capability, which may not permit realistic levels of noise and vibration symptoms. Industry is currently addressing these concerns to enhance the simulation realism for such failures. This video is intended to provide general information on the characteristics of some high bypass engine failures and malfunctions. It is not intended to be an in-depth study of all possible engine failure modes. Specific remedial action to be taken in the event of an engine failure is published in the Airplane Flight or Operating Manual.
An engine 1 or 2 control A or B degraded, or an engine 1 or 2 short dispatch advisory message indicates that a dispatchable MMEL Category B FADEC fault has been detected. An engine 1 or 2 idle stop fail advisory message indicates that the idle stop has failed. This concludes the power plant module.